In this lecture, we talk about algebraic extensions. So say you're given a field extension like this, E over F, and alpha is an element of a E. Then this element alpha is called algebraic over F if alpha is root of some non-zero polynomial in f of x. Now if alpha is not algebraic, that is, it is not root of any polynomial in f of x, then it is called transcendental over f. So you take this field f and you adjoin to it some alpha, then this is just called a simple extension. So you're just adjoining one element to it. Now this field extension E, this is also called algebraic extension of f if every element of E is algebraic over f. Now, and if E is not algebraic extension, it is called transcendental extension over f. So this is a lot to say. So what we are trying to say is that there are some elements alpha which lie in the extension field f, and there are some polynomials f which are part of f of x, that this f of alpha is 0, that alpha is the root of this polynomial f. But there could also be elements which are not roots of any polynomials. For example, pi is transcendental, so there is no polynomial f that you can write f of pi is 0. So pi is not the root of any polynomial. So now consider the evaluation map. So this evaluation map goes from f of x to, say, extension field E. So you have this map, you have f of x on one side and you have field on the other side, E. And this evaluation map is E of A. That means you take a polynomial here f of 1, you evaluate it here. So this will give you a number. Once you put a number a in it instead of x's, you will get a number here. So this number lies in E. So again, take a polynomial f2 here. This will get evaluated to f2a. f3 here, this will get evaluated to f3a. Now if kernel of E alpha is 0, so that is only 0 gets mapped to 0. So that is, there is no polynomial f1, f2, f3 or any polynomial here in f of x for which f1a, f2a evaluation is 0, because only thing is kernel is 0. None of these polynomials lie in the kernel. That means a is not the root of any of these polynomials. So therefore a is transcendental. So it is not the root of any polynomial. And then obviously you will have f of a equals to f of x. So these, look at these brackets. So these brackets are not square brackets, they are round brackets. So what does, and this is a square bracket. So what does f of x mean? So this is nothing but fractions like this, f over g, where f and g are both in this. So these are both polynomials, and this is just a fraction of polynomials. So notice that this would make sense, because once you plug in a here, the denominator is never 0 because a is transcendental. So g of a would never be 0. So you can interchange x and a. So you can go to field of fractions here if a is transcendental, because the denominator will always make sense. It is not going to vanish since a is not 0 of any polynomial. So a is transcendental. Now on the other hand, if kernel of EA is some polynomial f of x, so you take an irreducible polynomial here. So irreducible monic polynomial. So there is some polynomial here f which becomes 0 if you evaluate it at a. So obviously some polynomial like x minus a could be there, x minus a cube could be there, and so on. So what you take is an irreducible polynomial. And you know that irreducible polynomials here within the fields are maximal. So if you modulo out the maximal, what you will get is a field, and this field you write it as f of a. And obviously this f of a is 0, just like here, f of a is 0. Now this field you can obviously see because you are modulo outing by a irreducible polynomial which is maximal, but you can see it directly also. So say you take some polynomial here, say h of x. So if this h of x is non-zero, it has to be co-prime to this f of x, because this f of x is just 0 in the string. So since this is co-prime, then you know that you can find polynomials a of x, and then you have f of x, b of x equals to 1. So this is because h of x and f of x are co-prime, so this holds. So now you evaluate it at a, this portion will become 0, so this is equal to 1, and therefore this is the inverse. So this is inverse. So therefore anything you have here will have an inverse, so this becomes a field. But you can also see your modulo outing by a maximal ideal. Now if this field extension is finite, this would imply that E is algebraic extension of F. So say E is to F is M, then this set 1, B, B square all the way to Bm, this has M plus 1 elements. B lies in E. So obviously this has to be linearly dependent because this extension here is M and you have M plus 1 elements. So you find some Ci lying in this base field F so that this is 0. And obviously now you replace this polynomial with this polynomial, replace P with X. So now call this polynomial as P of X. So this entire thing is P of X. And this is P of B. And this obviously will be 0 precisely when you have P of B here. So instead of X you put in B, you will get this, which is 0. So now you have this polynomial P of X. So now you can construct your field extension. Your field extension is just E is equal to our f of x, and you modulo out your polynomial here. So this degree of this polynomial is m. Now you obviously know that this is generated by 1 x bar square all the way to x bar m minus 1. So m terms, including 1, you have m terms, which is the degree here. So degree of px is m, is equal to this extension degree, which is equal to f of p to f. So this is just a simple extension. Notice that this is a simple extension, but the degree is m. So thus we get a new definition of being algebraic. So alpha is algebraic over some field f if f of alpha is finite, because you ultimately need to find a polynomial whose 0 alpha it is. And so since you need to find a polynomial which has a root alpha, this polynomial would have a root alpha, only then alpha is algebraic. So then the degree of the polynomial basically gives you degree of the extension. So degree of the polynomial will give you the degree of extension. So you adjoin alpha, and rather than looking at this root, you basically look at the corresponding polynomial. So this is a new definition which is very useful. So alpha is algebraic over f if and only if f alpha over f is finite. Obviously if alpha is not algebraic, that is if alpha is transcendental, then f of alpha to f is infinite, because basically there is no polynomial here. You can also see it from here. So we wrote before that f of x over f is also infinite. So this is same as this. So you can see this because the basis for this is now 1 x square x cube all the way. There's no finite end to it. So this is for transcendental elements. If this alpha is transcendental here, then this will be infinite. So note that algebraic extensions may not be bounded. So this is difference between algebraic extensions and being algebraic. So E is called algebraic extension of f if every element of E is algebraic over f. So notice that this extension q, 2 to the power of half, 1/3, so all these elements you can adjoin, which are zeros of certain polynomials. So you can always have x square minus 2, x cube minus 2, and so on. So this is a algebraic extension which is not bounded. So you can see there are too many elements here. So there is a single element here, there are too many elements here. So this is a point of confusion, difference between algebraic and algebraic extension. So algebraic extension has every element has algebraic. So every element, so there are large number of elements. So now we do another theorem. So algebraic over algebraic is algebraic. So E1 is algebraic extension of E, and E is an algebraic extension of F. Then E1 is an algebraic extension of F. So we are given this E1 is algebraic over E, and this E is algebraic over F, and we want to show that this E1 is algebraic over F. So we don't want to go this route, we want to go this route. So you start with alpha 1 here, you adjoin some elements over F, and then show that alpha 1 is algebraic over F. So alpha 1 lies in E1, and it is algebraic over E. So this is algebraic over E. So there is a polynomial like this, so that f of alpha is 0, and each of these ai's lie in E. So now we will construct a sequence of fields which contains these coefficients. You adjoin them to the base field f, each of these coefficients, and then you will see that f of alpha is 0 in the field which has all these coefficients, because obviously everything depends upon this polynomial. So you plug in alpha in this polynomial would be 0. The only problem is that these ai's lie in E, they do not lie in F. So simple strategy is to put all these elements in F, that is adjoin all these elements with F. So you construct a new field A0, A1 all the way to AN, and this new field will have all the coefficients. It obviously has an x because this f of x will now lie in this field, and alpha is algebraic over this. So you are done. But we want to do this step by step, so let us do this again. So first you construct this field. F of 0 is f of A0. So you say this is algebraic because E is algebraic over F. So this A0 which lies in E, AI is in E, would be algebraic over F. So you can construct this F0 as an algebraic extension. So F1 is f of A0, A1, two coefficients, Fn is A0 to An. So this degree is n, Fn of alpha. So Fn is you adjoin everything. So this you are calling as f of n. So you adjoin everything. So Fn alpha over f is n, and this n is precisely because this is the degree of this polynomial here. And since each ai is algebraic over f, you get this Fn. This n is just, you just multiply by the multiplicative rule to get this. So Fn alpha over Fn, this over Fn minus 1, this. So every time you're just adjoining one more element. So first extension you adjoined A0. So this already has A0, you adjoined A1 here. So here this already had An minus 1, you adjoin An here. And finally you show that this is algebraic because of this reason here. So this is algebraic precisely because Fn contains all these elements and f of alpha is 0 for this polynomial, because this Fn will contain this polynomial, this ring would contain this polynomial, and f of alpha is 0, so this is also algebraic, and you have this degree as n. So basically this gives you the proof for algebraic extension over an algebraic extension is algebraic.